This is Physics 1C for November 1st. Today we're going to be talking about some more applications of magnetic forces. Specifically, we're going to discuss how you can create a torque on a coil that carries current using a magnetic field. And then we're going to use that to explain how an electric motor works. And from there, we're going to go into talking about where magnetic fields come from, the sources of magnetic fields. By using something called the Biot-Savart law, we'll describe how a current-carrying wire can produce a magnetic field, how big the field is, and we'll look at specific arrangements of wires. And so that is the goal for today. Just to remind you what we did last time, we learned about the magnetic force, and we said that the magnetic force is given by an equation where if you have a charged particle that has a velocity v and it's moving through a magnetic field, that as long as there is a component of the velocity that is perpendicular to the field, then you will get a magnetic force acting on that particle. That means that if the particle moves in the same direction as a magnetic field, it feels no force. If the particle has no velocity, it feels no force. The other thing that we learned is that if you have a current-carrying wire that has that's placed into a magnetic field, that current-carrying wire will also feel a magnetic force because the current-carrying wire is, after all, made up of little charged particles that are moving along with a velocity. So you can have a force on a wire as well that's given by the current in the wire times the length of the wire cross product of the magnetic field. Now, in both cases, we can talk about this force as being a small amount of force. And if we do that, if we want to look at just the small amount of force on a very tiny piece of wire, then we can come up with this expression that the force is going to be dl cross b. And we're going to use this to solve the problem that's over here on the left. So I wanted to show you how to do this. Oops. Okay, so we have a wire that's shaped like this. There's a straight segment of the wire here where the current's flowing left to right. And then there's a curvy section of the wire right here. So a semicircle with a radius of r. And there's a magnetic field that is pointing like this. Can anyone tell me, is this magnetic field pointing out of the page or into the page with all of these little dots right here? Is that out of the page or into the page? Out of the page, that's right. Remember that x is in, dot is out. Okay, so the magnetic field B is uniform and perpendicular to the plane of the figure pointing out of the page. The conductor carrying current I to the left has 3 segments. One straight segment with a length L perpendicular to the plane of the figure. So that's this. So it's coming into the screen, right? So current comes from the back into here, and then it goes up this way. Okay. 2, a semicircle with radius r, that's here. And then 3, another segment with a length L parallel to the axis. And what we want to do is to find the total force that's acting on this wire right here. So let's go one segment at a time. The first segment is the segment where the current is going, it's actually going into the page, I'm sorry. The current's going into the page right here. So if we have a current that goes into the page this way, and we have a magnetic field that points back out of the page this way, what's the direction of the force on that one going to be? Or what's the size of the force on that one going to be? On this first segment right here. Wait a minute, how is the current going in? Oh, it's coming out from here and then going in. That's what's happening. Okay. What's the direction of the force on that piece going to be? This piece of wire that comes into the screen like this right here. What's the angle between that wire and the magnetic field? We'll call that segment 1, segment 2, and segment 3. Segment 1, what's the force? The current going in, magnetic field's coming out. What's the angle between the current and the magnetic field? 180 degrees, right? So when we do our force equation here, we're going to get current multiplied by the length of that wire times the magnetic field times the sine of 180. And the sine of 180 is 0. So there's no force on that one. Any questions about that? Any questions about that? Okay, now segment 2 is a little harder, so let's do segment 3 first. So for segment 3, the current is flowing in this direction. So the length vector points to the left. And the current's coming out of the screen. So we can use our equation. And we can say that the angle between L and B is now going to be 90 degrees. L is this way, magnetic field is out. So the angle between those two is going to be 90 degrees. So this is going to be ILB times the sine of 90. So it's just going to be equal to whatever the current is, multiplied by the length of the wire, which is called L here, and then multiplied by the magnetic field B. And this one's going to point up. And that's because, to remind you how we do this, we use the right-hand rule. You point your fingers in the direction of the current, face your palm in the direction of the magnetic field, which is out this way. Your fingers should curve from here to here, with your thumb pointing up. Okay. So now let's go to the harder part of this, which is this section right here. Now there's a lot of stuff that's already been drawn in here, and I always personally find that to be kind of confusing when I'm addressing these things. So I'm just going to draw my own little wire here. Make it yellow just like it is in the picture. And make it roughly the same size. So we can compare our drawing to that one. All right, so this is our wire, but we only need a portion of it. So we're going to erase the bottom half. So we'll go from here, erase all of this up to here. So there's our wire. It carries current. The current is flowing in this direction. And the magnetic field, I'm not going to draw the, well, I guess I could, but you can just remember that the magnetic field's coming out of the page. The origin is about here. Okay, so we'd like to find a way to find the net force on this wire. And we're going to do that by breaking up the wire like this. We're going to find the force on just a small portion of it, and then we'll use that to sum up and find the total force acting on the wire. So first things first, we cut out a little piece here. And we're going to say that our piece here has a length that we're going to call DL. The current is uniform throughout here. So you may be wondering, oh, why don't we talk about the current DI? Well, the current is the same all through here. Okay. So we cut out a little piece that we call DL. And then we draw a line from here to here. That line is going to have a length R. And let me write that on this side. Length R like this right here. And what we need to do is we need to figure out the force on just this one piece. Now, in order to do that, put this down just a little bit here. We need to think about what the direction of the force is going to be. So use your right hand, point your fingers in the direction of that vector there. So like that, right? And then wrap your fingers in the direction of the magnetic field. The easiest way to do that is to point your palm in the direction that the magnetic field is. The magnetic field's coming out of the page like this. And then wrap your fingers from DL to B. And when you do that, your thumb should be pointing up and to the right. Make sure you can all do that. So DL cross with B, which is out of the page. Can everyone see then that you're going to get a force vector that points like this? Basically perpendicular to the surface of the, not the surface, but the edge of the semicircle. Everyone agree? Can you all see that? Okay. Now, we know that that force vector is going to have components. You can see the components in the picture over there. We'll redraw them here as well. Just like this. We can break this vector dfb up into two components. One that's going to point in the x direction like that. And then one that's going to point in the y direction like this. And we can call those, dfy and dfx. like that. And we can consider what happens if we were to come over here and look at another piece of current DL. If make sure, assuming that we come to exactly the same angle theta, so let's call this angle theta right here. Assuming that we come to the exact same angle theta on this side, know that it doesn't look like it, but well, in fact, it doesn't look like it, so let's make it look like it. Okay, so this is here. This is dfx. Let's draw a line from here to here. And then let's label this angle right here to be theta. And then let's come into the exact same angle theta on this side. Should be something like that, maybe, right? And then let's draw another DL. That's not quite right either, is it? It's just a little bit bigger, something like that. That seems fine. So if we call that theta, we draw another DL vector in here. Can you all tell me what's the direction of the force on this DL vector going to be? So magnetic field's coming out of the page, right? The DL vector is going down this way. What's the direction of the force on that vector going to be? Up and left. Do other people agree? Use your right hand, point it in the direction of DL, rotate your fingers to B. DL is this way. B is this way. Your thumb goes this way. So you should be able to verify that the force vector in this case also points up and to the left. And what that means is that if I have these two vectors and they truly are exactly equal to each other, what does that mean about the way we... Ultimately, what we're going to be doing here is we're going to be adding this vector plus this vector plus whatever the vector is right here, plus whatever the vector is right here. We're going to have to add up all these vectors together, right? And adding vectors is really quite time-consuming. But in this case, I think we can make some assumptions about how the way those vectors are going to add up. What can we assume? When I go through and I add up the DFBs for every single one of these, ultimately we're going to be summing up all of our DFBs, right? And when we do that, what's going to happen? Can you all see it? Do you need me to draw more lines on here? What kind of simplification can we make? Evan says only the y component matters. The x ones cancel out, yeah. Because if we were to draw the x component for this one, you'd have a dfx going this way. And we'd have our dfy going up this way. And so now this dfx and this dfx should be equal and opposite to each other. So we can say that all of the dfx's are going to cancel. Some will be positive and some will be negative. And of course, we've seen this happen pretty frequently when we do derivations like this, and this won't be the last place. So given that that's the case, we know that our force is going to be found by just finding the dfy's, and the dfy's are going to be equal to whatever the magnetic force is multiplied by, if this angle is theta and this angle is theta, what should I put here, sine or cosine? if I want to get the y component, and I know that dfb is the length of this vector, I have to multiply by sine of theta. That's right. Okay. Now, we know that the size of dfb is I times dl times b multiplied by the sine of the angle between dl and db. What's that going to be? So these are two different things. The sine of theta is still out here, okay? But when I do this equation, this is the same thing as saying I dl b times the sine of the angle between the dl and the b, right? So what is that here? What's the angle between dl and the magnetic field? What angle goes right here? 90 degrees, exactly. Because dl is in the plane of the page, the magnetic field comes out of the page. Any vector that I draw on this plane, this vector perpendicular to the magnetic field, right? This vector perpendicular to the magnetic field. Any vector I draw in this space is guaranteed perpendicular to the magnetic field. So that dl also perpendicular to the magnetic field, which is coming out of the screen. Great, so that's sine 90, and that's 1. That's super simple. We don't need to do anything with that. So now what we're left with is I times b times the sine of theta, and then we have this dl thing that we got to deal with, right? Now, what we can say in our picture here is that dl, at least the magnitude of it, I don't know, you all tell me, what should I put in there for the magnitude of dl? It's a segment of a circle, right? 2 pi dr? Yeah, I think that Ton is right. We want to do rd theta. Our dl vector is basically kind of like an arc length. And why do I say that? Well, because it's the length of a piece, right? And that's like an arc. It's like the arc of a circle. What's an arc of a circle? Well, that's an arc, right? An arc is a segment of the circumference of a circle. So dl is like an arc length, and you probably remember this relationship, that the arc length is equal to r times theta, or if in this case we have a d theta, which is drawn in this picture right here, the change in theta, d theta, then you can say that the arc length dl should be equal to r times d theta. Anyway, it's just another way to express. This is just something, you learn this, I don't know, probably in Algebra 2, right? Or trig or something like that. You learn about this relationship, and we can do the exact same thing here. Okay, so we can replace our dl with rd theta. Does anyone have any questions about that? Okay, so we're going to replace dl with rd theta. Okay. And now we can integrate both sides, because current, magnetic field, and radius are all constants and can be pulled out of the integral here. So we just end up doing the integral of sine theta d theta. What should I use for my limits? Zero to pi. Okay, because the angle theta goes from, a small angle like right here, because we basically have to break the entire thing up into a bunch of little dl's, right? That's what we're doing. Okay, so we want to go from the smallest angle theta, which would be down here, to the biggest angle theta, which would be over here. So from a little angle all the way to here. So from theta equal to 0, remember this is theta, up to theta equal to pi. Okay, and that's an easy integral to do. So maybe we recenter our thing here. So we have Fy, which is going to be the total force on the semicircle. Should be equal to I, B, R, and then when we integrate sine theta, we're going to get what? It'd probably be a little faster if you just cued your mic and answered. You all can talk. You don't have to be so quiet. You're welcome to type in if you don't want to talk, but anyone want to queue up and just say what the answer to this is? What's the integral of sine theta?
Negative cosine?
Thank you. So negative cos theta. Then we have to integrate that from 0 to pi. We plug in our limits, so we'll have negative cosine of pi minus cos 0. No. Minus cos 0. There we go. That's better. There we go. And that should give us, I think, negative of -1 minus -1 is going to be 2, right? So we're going to get 2 times I times B times R. Does anyone have any questions? We needed to find the total force. So we're going to have to add this to the force on this part. So we need to add to this the force on part 3, which is going to be equal to just ILB. So the total force is going to be equal to 2IBR plus ILB, and it points up. Does anyone have any questions? No? It all makes sense? It's all just really clear? We ready to go on to talking about torque then? Okay. So let's talk about the torque on a loop of wire that carries current. Sorry, I put down my pen again. Oh, there it is. Okay. So suppose we have a situation like this right here. we have a loop of wire in the shape of a rectangle, and it's placed into a magnetic field. The magnetic field points all the way throughout here. Okay, so just imagine this magnetic field continues through. It's just not drawn there in order to kind of keep clear about what's going on. So we have a loop of wire. It carries an electrical current. So we've got electrons and they're moving around here. The loop has dimensions of A on this side and B on this side. And we would like to find the force on each segment and then find if we can create a torque on this object. So first we want to find the force on each segment. Okay, so to do that, we have segment 1, segment 2, segment 3, and segment 4. Can you all tell me, for any of these sides, which ones are the force going to be equal to 0 and why? Side 1, 2, 3, or 4. Which sides are going to have a force equal to 0? One and 3, right? So the answer is 1 and 3. And the reason why is because, why? What was the reason? The vectors are either parallel or anti-parallel, exactly. Current here goes against the magnetic field exactly. The current in segment 3 is parallel to the magnetic field, so that also means, as Kyan said, that the angles are going to be 0 and 180. We take the sine of 0 or the sine of 180, you get 0. Okay, so we know that only 2 and 4 are going to feel force. So what kind of force are they going to feel? So the force on side 2 should be equal to the current flowing through that segment multiplied by the length of the segment, which is A. Right? A is the length of the segment. Again, we're using this equation, FB equal to IL cross B. All right, so that's our equation. So we take current times length, and then we multiply by the magnetic fields. And now we got to figure out the direction. Can you all tell me, what's the direction of the force here going to be? Is it going to point to the left, to the right, up, down, out of the page, into the page? What's the direction of this force? Out of the page. Okay, so if you take your fingers and you point in the direction of the current, which is going down, wrap your fingers toward B, your thumb should point out of the page. So we're going to label that as a dot with a circle. Out of the page, right? On F4, the current is going to be I, same current flowing through the whole thing. The length of this wire right here is also A. And we multiply by the size of the magnetic field, which we're just calling B. And now what's the direction on this one going to be? Out or in? This one should be in. Your fingers point up for the current. You face your palm in the direction of the magnetic field. Magnetic field's going that way. Rotate your fingers this way. Your thumb goes into the page. So the direction for this one is into the page. Okay, so now suppose that we take our entire object and we run a hole, we cut a hole in this piece, we cut a hole in this piece, right? And then we shove a long, skinny piece of metal through here to mount it on, okay? If we know the force on side 2 is coming out of the page, right? There's a force coming this way. And the force on this side is going this way. Then that's like saying that our thing is being it's being turned like this, almost like a revolving door, right? This side it's being opened, that side's being kind of closed in this way, and the whole system, if we were to place if we were to give it a way to rotate by cutting a hole in the top and a hole in the bottom and then sticking a needle through here or something like that, then the entire thing would now feel a force that would cause it to rotate at least up to a certain point, okay? And I'm going to scroll down right here because that's what's shown right here. Make this a little smaller. Oh no. I'll have to get rid of this stuff. There we go. Okay. So that's probably being blocked off. Let me move this over to this side now. That way it won't get blocked off. Okay, so Suppose then that we take our entire system, right, and we twist it so that we're looking at it from the edge on. So this would be side 3 right here that we're looking at. This is side 3, this is side 2, and this is side 4, okay? So now side 2, the current is coming out into the page, and side 4, the current is going, current's out of the page for side 2 and into the page for side 4 now. And we've redrawn our forces because here, the direction of the force on this one was up, the direction of the force for this one was into the page. So out of the page, into the page, now becomes, when I take the entire thing and I switch it up on its edge like this, now the force on F2 is up, and the force on F4 is down. Can you all make the connection going from this picture to this picture? It's just been flipped. It's like you take the rectangle, and now you're looking at it on its edge. Okay. Now, if we do that, and we make a hinge of some sort, something that'll allow the object to rotate about this, we create an axis. So we basically put a rotational axis at O, right there in the center. Then there's going to be a net torque Hey, how am I doing on time? Really well, actually. Good. Okay, so we put a rotational axis at O and allow the loop to rotate. The magnetic field is now pointing to the right, and it's now free to rotate. We can calculate what that torque is going to be. So the net torque should be equal to F2 multiplied by the distance from here to the axis, which, since we're saying that this object is B, or the length of this side, side 3 is B, then the distance from wire 2, or the left side of the loop, to the center is going to be B over 2, plus F4 also multiplied by B over 2. And if we plug in the values up here, we have I times A times B over 2 plus F4. It's going to be I times A times B over 2. And then put them all together, we end up getting that the net torque is equal to I times A times B times B. But what would A times B represent in this case? This is the area of the loop. So let's call that capital A. And now our net torque is equal to current times area multiplied by magnetic field. This is actually going to be defined as the maximum torque, because as we will see in a second, the torque is going to get smaller. But notice the result is quite simple. It's current times area times magnetic field. Current times area times magnetic field. Pretty simple. All right. Now, the next thing to do is to think about what happens when this system has rotated a little bit. So we'll draw our own picture for this. So the book, your book, uses this three-dimensional picture that I personally think is a little bit hard to understand. So what we're going to do instead is, this is going to be our wire. We'll make it a different color than the writing that we're using. Maybe put it right here. It's going to be hinged in the center again. And we're going to have current flowing. Here, let's make the wire have some thickness to it. So here's our wire. Again, this is side 3. And it's hinged. Again, we're going to be saying the current is flowing towards us here. So that's the current there. There's current flowing, this current is flowing towards us. This one's flowing in. Now, what's going to happen to the direction of the forces? Now, what I'm thinking about here is that the system is rotating like this, right? So I'm going to just allow it to rotate up to a new point, and we're going to look at the forces again and the new torques that happen as a result of it. What's going to happen to the force on this side over here once it's rotated. If the magnetic field is still pointing in this direction, so if this is still the magnetic field direction, I probably shouldn't do it like that. Let's just say magnetic field points this way, right? What happens, and the current, this is current. This is current as well. And there's, of course, current flowing along the wire as well. What's the direction of the magnetic force on side 2 over here? And this is still side 2. This is still side 4. Use your right-hand rule again. What's the direction of the force on 2 now? Has it changed? Does it point this way? Does it point that way? What way does it point now? How do I want to draw the force for side 2? Is it going to go straight up, straight down, to the right, to the left? What happens? Up and to the right, up and to the right. I see 3 different answers, 4 different answers. I see upright, and up. Doesn't seem like there's a lot of... anyone feel really confident about this? So you all think it should go this way? Or when you said upright, did you mean like 90 degrees? Or like 45 degrees? Like more like this? And how did you get that answer? Perpendicular, so you think it's like this? So you're saying if you do I cross B, that's the direction your thumb points. Try it with your right hand. Take your right hand, point your fingers in the direction of the current, rotate your fingers from the current to the magnetic field, and tell me what you get. Maybe some people that haven't answered the question already can try to chime in and tell me what they get. Josh, you got straight up. So now we have 2 people that got straight up and 3 people that got something else. If this was a democracy, I guess it would be up and to the right, but it's not. It's a question of what's the right answer. Is anyone strongly convinced and want to argue further on their point? Anyone else that hasn't answered yet want to try to answer? What's the direction of the force on wire 2? Anyone can type out a reason why would be helpful as well. To where you can write an answer and you can confidently state why. If it's out of the page, shouldn't it be down left? Okay, so now we're thinking that it's now you're starting to think that it's this way, huh? Nope, seems like we're getting more confused. Okay, T-Lim says, with the right-hand rule, your thumb goes with B. The others go out of the comp is for when I re-roll. Should it be straight down? Your thumb doesn't go with B. Your thumb is where the force is. Your fingers go with I, and then your fingers wrap from I to B. And your thumb points in the direction of the force. The L vector points in the same direction as I does. Seems to be a lot of confusion. I don't see anybody that's confidently giving an answer. Someone that says, hey, I know it's this and this is why. That's what I'm waiting for. And I'm just going to wait because I don't see any point in continuing with this if you don't understand the directions. And while some of you have gotten the right answer, some of you have gotten the wrong answer, and there's clearly a right answer, and I'd like to see someone like confidently state why they think their answer is right. Or maybe confidently disprove some of the answers that have been given, because there's definitely a way to do that too. What direction does it point? Down leftish. You know if it helps, but the force went straight out. So you base it off that. You should base it on the right-hand rule. Is the question I'm asking clear? So I have a current that's coming out of the page, right? The current points this way. Magnetic field points that way. And we need to figure out the direction of the force. That's the question. What's the direction of the force on this piece right here? Brandon says it straight up. Ton says in. East, north? No. Okay, let's go back to the assumption that some of you made, which is that it's going to point up and to the right. Which it seems like is what most people are saying. So this is the answer that it seems like the majority of people have given right here, right? Is there anyone at all that understands this well enough that you can prove to me why that's wrong? And it is wrong. Why can anyone prove to me why that's the wrong answer? Why is this the wrong answer? You're right, Josh. The correct answer is straight up. I want someone to prove to me why they know that this is not a good answer. Why is this not the right answer? What is there if you look at this equation that it tells you that that can't be right? So just to be clear, the correct answer is straight up. Seems like nobody was able to figure this out. I don't know why. I don't think this is particularly challenging. That's right, Josh. If you do this, and this is your magnetic field, then these are not perpendicular to each other. And according to this equation, what this equation says, not just in math, but in words, is that you find the magnetic field by taking the cross product of L and B. You find the magnetic force. The magnetic force then has to be perpendicular to L. It also has to be perpendicular to B. Right? Does that make sense? L and B create a plane. The magnetic force has to be perpendicular to both of them. And so you can see that this, if you make the magnetic force point up and to the right, then this angle is definitely not a right angle. There's only one direction for a vector. There's two. There's two possible directions for a vector that's perpendicular to both of these, either this way or this way. And the right-hand rule tells you which of those is the correct answer. Basically, if you look at it, the current comes out of the page. The magnetic field is going this way, right? So those two vectors, they form a plane. Any two vectors can form a plane, right? If I have a vector that points this way and a vector that points this way, they make a plane, the plane between them. And the force you create here has to be, or the force you construct here has to be perpendicular to both of them. You'll need to figure this stuff out. This is one of those things where I'm not always going to slow down this much to make sure everyone understands what's happening, because we're just going to be doing kind of trickier things. You have to, you should trust yourself. Trust yourself and trust the ideas, right? The idea in this case is the right-hand rule, right? Don't try to overthink it. So the magnetic force is straight up, and again, if you can't do that yourself, you need to be able to do what I'm about to do here. So you need to be able to say that if you take your hand and you point in the direction of the current, which is this way, and you curl your fingers to the direction of the magnetic field, which is this way, your thumb points straight up, not at an angle. So if you've got an answer where your thumb is pointing at an angle, you're kind of putting something into it that's not part of the rule, and you need to stop doing that, or you're going to confuse yourself. All right. So side 4, what happens? So now again, let's go back to what we're doing here. We have a loop. It has magnetic field flowing through it. We figured out that there's this kind of effect where one side has a force that comes out and one side has a force that goes in. So we said, suppose that we turn it on its edge and we run an axis through point O that goes through the entire loop. And now we allow the loop to rotate. What's going to happen is that the loop is now going to rotate a little bit. It's going to rotate clockwise because the torque is tending to move it clockwise. And we found that after it's rotated by some angle or so that now that it's at an angle like this, we're looking at the forces on each of the sides, and we found the force on the left side was pointing straight up, like that. And I guess we should probably call it F2, because there's also going to be another force on the other side, right? So we'll call this one F2. Okay, now that we went through all that discussion, can you all tell me what's the direction of the force on this one going to be? Do I cross B again, right? I is into the page, B is to the right. You all tell me what's the direction that your thumb points. Point your fingers into the page. Wrap your fingers to B. Your thumb should point down. If right now you're sitting at your desk, either ignoring me or not doing what I'm doing with my hand, then you're not learning anything. You know, you have to actively be doing things while you're learning in order to actually learn something during class. You're not going to get much by just sitting there. You know what I mean? So when I say you need to point your fingers this way and wrap them this way, you need to be doing that too. And if we were in a classroom, I could point out and call on people that weren't doing it. I can't do that now because I can't see you. Yeah, if it breaks your wrists, you need to probably turn around. You know, you can turn your body around sometimes, and that might make it easier on you. This one is this way. This one doesn't hurt my hand, but I guess it depends on how you're doing it. Anyway, so here we're going to get a force, and it's going to point down. And again, like I say, every time that I say you need to do this, you need to do it, because you're only going to get better at this by practicing. And it's pretty obvious from the responses that I've been getting that either 80% of you just aren't here and aren't paying attention, and aren't getting involved, or you just don't understand it. I'm not sure which one it is, but either way, you're not helping yourself out. Okay, so we've got this thing, it rotates. We now know the direction of the forces. We notice that even if it rotated a little bit more, the forces would still be pointing straight up and straight down. And the next thing that we can do is we're going to draw a line in here, straight across like this. Center it right in the center. And now let's label the angle through which this has moved by drawing one more line, another vector, maybe with green, from the center, perpendicular, okay, we're going to draw, we're going to make a perpendicular line, and then we're going to call this angle right here phi. All right. And then we're going to try to calculate what the torque is in this section. So now we want to find the torque. So the net torque now is going to be equal to F2. If I want to find the torque from force 2, I need to take this distance right here, which is B over 2, and then I'm going to drop a line here to make a right angle and say that if that angle right there is phi, then this angle has to be 90 minus phi, which means this angle at the top here is also going to be phi, which means that the length of this side right here is B over 2 times what? Sine or cosine of phi right here? If the upper angle is phi, should this be B over 2 times what? Sine or cosine of phi? Cosine, sine. Okay, well, no, that doesn't help. Sine. It's opposite, right? That's phi. We're opposite, so it should be sine. And we can construct the exact same triangle over here on this side. So drop a right angle right there. This is B over 2, so I'm not going to draw it, but this side right here would also be B over 2 times the sine of phi. All right. Torque is defined as force times lever arm. So this is our lever arm. So we multiply by B over 2 times the sine of phi. And then we add to that the torque from F4. So plus F4 times B over 2 times the sine of phi. Now, what happens to the size of the force? Does the size of the force change? Did any of these three quantities change here? Or did the angle between the length and the magnetic field change? Did any of those quantities change? Is the current the same? So what angle is this? What is the angle that's contained inside of here? The angle that shows up in here, so I'll write it down like this. It's ILB sine of some angle. We'll call the angle alpha. Alpha is the angle between what and what? Angle between I and B, right. Technically, it's the angle between L and B, but whatever. Same thing. I and B, L and B, however you want to think about it. Okay, has that angle changed? Has the angle between L and B changed? What's the direction of L? Let's go back to our picture. L is in the same direction as I, right? So it's like this. The angle between L and B here is very obviously 90 degrees. If I take my system and I flip it up on its edge, like we've done right here, the angle between L, which now comes out of the page, so L is now coming out of the page, the angle between, well, you tell me here, what's the angle between L and B in this picture? $90, okay. So come over to this picture here. Here's the loop has now rotated a little bit, right? What's the angle now? I is coming out of the page. Magnetic field's going to the right like this. What's the angle between them? It's still 90, right? Everybody can see that, I hope. Okay. So the angle didn't change. Did the current change? Did the length change? Did the magnetic field change? Did any of those things change? No. So the force is still going to be IAB, because this was the force here. We said it was current times A times B, right? So it's the same again, right? So we have F2 is IAB times B over 2 sine of phi plus F4 is also going to be IA times B. Remember, A was the length of the wire. In case you forgot, A was the length of the wire from here to here. A. All right, so we do IAB and then times B over 2 sine of phi. Okay. So adding them up again, we get very similar result. I times A times B times B. The only difference is now there is a sine phi hanging out. And once again, we can change the A times B into the area of our loop. And this gives us the torque for any angle. What happens when the angle is 90 degrees? Sine of 90 is 1, and you get the maximum torque, right? What happens when phi becomes 0? What happens when phi becomes 0? No torque, yeah? Hopefully that makes sense, because you can imagine that once this thing rotates through 90 degrees, phi will be 0, right? Remember, phi is this angle here, so it's when it starts, phi is 90, like here, phi is 90 here, and then when it rotates, phi can become 0. Once that occurs, the loop is going to be like this. F2 is going to be up this way, and F4 is going to be down this way, right? So no torque now. Because phi equal to 0. Okay. So what can we take away from this? We can take away from this the fact that if I were to take a loop and I were to orient it like this, and I put it inside of a magnetic field, right? If you flow current through the loop will basically eventually go from this position into this position, right? It's like there's some energy that forces it to go from this horizontal to the kind of straight up and down. But then at that point, it would kind of stop moving because now it would be balanced. But you can see that it would undergo this quarter turn just from the fact that there's current flowing in the loop. Now, one thing that we can do is suppose that our loop had more than one coil to it, okay? So if you have N loops of wire, okay, what would that look like? That would be like we have one loop, and then on top of that loop, we take another piece of wire and we just keep wrapping loop on top of loop, on top of loop, on top of loop. So you basically just take one piece of wire, turn it into a rectangle, and then just have bunches and bunches of loops of wire all on top of each other. You form this same loop, right? Then for every loop that you get, you're going to increase the torque because each loop is going to have a contribution of IAB times the sine of phi. Okay? For N loops of wire. And then what we're going to do is we're going to take this right here and we're going to say let this symbol represent, so mu is the symbol. It's equal to the number of loops times the current multiplied by the area of the loop. And we call this magnetic moment. This is called magnetic moment. Is it magnetic dipole moment or is it just magnetic moment? It's both. It's magnetic moment or magnetic dipole moment. You'll see both of those terms show up. And it can be written as a vector. I'll get to that in a second. But just so you know, the magnitude of this is number of loops times the current multiplied by the area. We can turn it into a vector, not by, so look at these pieces. Current is not a vector. Number of loops is not a vector, but we know area can be a vector. So we can define the magnetic moment like this if we make the area of the loop into a vector. And the area isn't dipole kind of redundant since magnets are only dipoles? Yeah, maybe so. So how do we define the direction of this? Well, that's where we go back to this picture right here. So I drew this vector on here, but I didn't label it. I'm going to go ahead and label it now. This is going to be our area vector. And I'm going to show you how you actually figure out the direction of the area vector. So that's our area vector, but it turns out that that's also the same as the direction as the magnetic moment vector. Okay. They don't have the same size, but they point in the same direction. So now what you do to figure out the direction of your area vector is you basically sweep your fingers around the current, like around the direction of the current, okay? So can you tell that if I point my thumb this way, that my fingers in my hand basically sweep along in the direction that the current is flowing? You should try this yourself too. Take your thumb, point it along the direction of your screen where you see that area vector pointing. And then remember that the current is flowing down this way through that wire, and that, yeah, your fingers basically sweep around like this in the direction of the current with your thumb pointing up this way. I'll give you some more examples so you can understand better what this means. So prior to doing that, I want to say that even though the derivation that we did was for a rectangular loop of wire, you can define the magnetic moment for really any loop of wire. It doesn't matter if it's circular or shaped in some other way. All you care about is the area of the loop itself. okay? So for example, if I had a wire and it carried a current like this, so here's the thing that's really cool about this, is that really any wire has a magnetic moment as long as it carries current. And what that means is that any loop of wire has the ability to be affected by an external magnetic field due to the fact that it carries current. Can you all tell me, if I have a current that flows around like this and it's in the plane of the page, what would the direction of the magnetic moment for this loop be? Just direction is all I care about. We don't care about the size. What would the direction of the magnetic moment, if the current is flowing clockwise like this, what would the direction of the magnetic moment be? To figure this out, you have to basically sweep your fingers around in the direction of the current, and it points out. That's exactly right. Hopefully you can see that, your finger, your right hand, it only rotates one way, right? I mean, you can rotate it backwards, but it's quite painful. Your hand closes in one direction, right? And this current is flowing around in a, what is that, counterclockwise? Yeah, counterclockwise direction. And when you swing your fingers in a counterclockwise direction, your thumb always points out. Can everyone see that? Okay. What if I have a current loop that does this? So instead of being in the plane of the page, let's say the current flows around this way and back that way, meaning that it's kind of flowing in a circle like this. What would the direction of the magnetic moment for this loop be? So this is like a loop that's like this. Current goes this way, you swing your fingers around like this, your thumb points up, right? So that's the direction of the magnetic moment vector. Okay. So let's take this a step farther. So these magnetic moment vectors are very similar to compass needles, okay? What do I mean by that? I mean that if I have, a compass. A compass is basically something that just has a little dipole magnet inside of it, right? So let's say that I have a compass, and let's say that this is the north pole of the compass, okay? Right? And now I come along and I put a magnet near this object, okay? And the magnet that I place near it makes it so that there's a magnetic field that points from left to right. So I put the compass in a region where there's a magnetic field that points like this. What is the compass needle going to do? So if this is the direction of the magnetic field, what do you expect the compass needle to do? It's going to point to the right. Can you say that in a more scientific way? I don't know if that makes any sense. The compass is it's gonna line up with the magnetic field, right? It's gonna line up with the magnetic field. It's gonna do exactly that, right? It's gonna go from here, and then it's gonna eventually rotate, and it's gonna line up with the magnetic field. Now, it might not just immediately line completely up with the magnetic field, meaning it might start like this. It might come to here and then wobble past and then wobble back and forth, but it will reach equilibrium when it lines up with the magnetic field, okay? So I can tell you that these little compass needles, they also have magnetic moments. And the magnetic moment of the compass needle points like that. It points in the same direction as the magnetic field points, okay? So loops of wire act like compass needles, right? Because look at what happened with this loop of wire. The loop of wire had a magnetic moment that was pointing up this way, right? And we said that given enough time, eventually that magnetic moment ends up pointing this way. And lo and behold, that's also the same as the direction of the magnetic field, right? So the tendency of a loop of wire that has current flowing through it is going to be such that its magnetic moment will want to tend to line up with external magnetic fields. Just like a compass needle does. Just like a compass needle does. Does that make sense? Okay, so last thing, torque was defined as NIA B sine phi. We said that we could define the magnetic moment as NIA. So putting these two things together, what we can do is we can say that the torque is given in a more simple way as the magnetic moment vector cross products with the magnetic field. Okay. That is our equation. Remember that magnetic moment is NIA. And I think we probably have to take a break now. Yeah. So let's take a break until 2:35. And then if you want to, you can look at this problem. This is what we'll be doing when we come back.